In this video, we're going to take a look at some examples of transformations and how we build matrix transformations for a variety of different transformations. So we're going to take a look at, first of all, a situation where we're going to take a three-dimensional vector as an input. And what we're going to output is a two-dimensional vector. So in this case, our transformation is a mapping from R3 into R2. And so this just means that we're going to take a vector that starts off in 3 dimensions. So we'll have a vector out here that starts off in 3 dimensions, and then the transformation is going to do something to it to put it into 2 dimensions. Now, there's lots of applications of this in the real world where we're taking 3-dimensional images and projecting them onto a 2-dimensional plane, so in things like computer graphics. All right, well, let's get started. So here we want to take this vector, and we're told that basically to build the matrix, that when it takes A times this vector that contains 3 components, x1, x2, and x3, that what it will output is in the x component of the new vector, it'll be 2x1 plus 3x2, and in the y component of that new vector will output 4x3 minus 2x1. Okay, so the vector that we need to look at first is the vector that we're starting with, which is this one. And in order to perform the transformation on a vector in R3, we need to construct the transformation of each of the 3 basis vectors in R3. So first of all, we have 1, 0, 0, and that's one of the ones that we need to transform. Then the other basis vector is 0, 1, 0, and the third vector is 0, 0, 1. So in 3 dimensions, these can be thought of as if this is x, y, and z, or x1, x2, x3, then the 1, 0, 0 vector is just a unit-long vector that points in the x direction. 0, 1, 0 is the unit-long vector that points in the y direction, and 0, 0, 1 is the vector that points straight up 1 unit. So to perform this transformation, we're told that what the output should be if we transform a vector is in the top component of the result, we should take 2x1 plus 3x2. So 2x1, that's going to be 2 times 1 plus 3 times x2, which is 0. So 2 times 1 plus 3 times 0 is going to equal 2. And for the bottom component, we want 4 times the x3 component, so 4 times 0 minus 2 times x1, which is 1. So we have 4 times 0 minus 2, which is negative 2. Now we're going to do the same thing to the 0, 1, 0 vector. So 2 times 0 plus 3 times 1 is 3. And now for the bottom component of this transformation, we have 4 times 0 minus 2 times 0, which is 0. And so basically, we can see here that the 1, 0, 0 vector gets mapped to the vector 2, negative 2. So that would be a vector that is 2 units this way, 1, 2, and 2 units down. So we'll get mapped to this vector. So this 1, 0, 0 vector here is going to get converted to this 2-dimensional vector. And this 0, 1, 0 vector right here, this is going to get mapped to the vector 3, 0, which is 3 units over, 0 units up or down. So it's this vector here. And for all intents and purposes, it doesn't really matter what this actually means at the moment. We're just performing a transformation. Okay, so we have one more to go. And in this example, we have 0, 0, 1. So for the output, we're going to take, again, 2 times the x1 component, which is 2 times 0, plus 3 times 0 is 0. And for the bottom component in our output vector, we have 4 times 1, which is 4, minus 2 times 0, which is still 4. And to form our A matrix, the one that's going to perform this transformation on a vector, we're going to take these 3 columns stacked in this order. So first, the transformation of 1, 0, 0, which is 2, negative 2. Then the transformation of 0, 1, 0, which is 3, 0. And then the transformation of 0, 0, 1, which is 0, 4. Now you can almost see what's happening here in the matrix. We see a 2 in the where if we multiplied this by a vector now, so if we took 2, 3, 0, negative 2, 0, 4 and multiplied it by, say, any vector, let's just go ahead and call it x1, x2, x3, just to show that the output that we get matches what we were wanting to get. So x1 multiplies the first column, x2 multiplies the second column, x3 multiplies the third column. So what we'll end up having is, and I'll just put an x here to make this equal sign true, we'll have 2 times x1 plus 3 times x2 plus 0 times x3, which is really just 2x1 plus 3x2. And then when we multiply the bottom components, negative 2 times x1 plus 0 times x2 plus 4 times x3, well, that's negative 2x1 plus 4x3, which is the same thing as 4x3 minus 2x1. And we can see that the transformation has been performed. So one interesting thing to note here is that A matrix had to be a 2 by 3. And the vector we multiplied by was a 3 by 1. And the output was a 2 by 1. So you notice here that the size of this matrix, the first component is going to involve the size of the output vector that you want. And the inner dimension here, 3, is going to represent how big the vectors are that are being multiplied. So we're going from R3 into R2. So we needed a 2 by 3 matrix to do this. So a real-world example where we might see transformations is in data analysis. We often want to calculate things like means about a data set. So suppose we have a vector of data in 4 dimensions. Now, a lot of times our data is going to be many, many, many dimensions beyond 4, but we don't have really the capacity to write that all out. So, and we want the output to be a value in R. Okay, that's R1. So we're going to take something that's in 4 dimensions and we're going to output something that is in 1 dimension. Sometimes people will, you can say R1, but usually just saying R is fine. Namely, the average of the 4 values, find the A matrix that will accomplish this task. So we have a transformation that is going to take a vector in R4, and it's going to produce a single value in just R. Okay, so what we need to first of all establish is that what we're looking to do is if X is this 4 by 1 vector that just consists of components x1 through x4, then we want the output to be x1 plus x2 plus x3 plus x4 divided by 4. That's how we compute an average. Now, another way we could write this is that we could write this as really 1/4 of x1 plus 1/4 of x2 plus 1/4 of x3 plus 1/4 of x4. And okay, so in order to conduct this transformation, we would need to build this matrix, we would need to perform 4 separate transformations on each of the standard basis vectors in R4. So it's going to have 4 components. The first one will be 1, 0, 0, 0. Then we'll need to compute the transformation of 0, 1, 0, 0. And then the transformation of 0, 0, 1, 0. And then finally the transformation of 0, 0, 0, 1. Okay, so all we're going to do is we're just going to apply this formula to each of these vectors. So it's not going to be too surprising that what we're going to get is 1/4 of 1 plus 1/4 of 2 plus 1/4 of 3 plus 1/4 of 4. Or really, if I just add up these 4 values, I'm going to get 1. 1 plus 0 plus 0 plus 0 divided by 4 is just 1/4. Okay, now notice we did transform an R4 vector into an R value. And same thing is going to apply here. The average of 0, 1, 0, and 0 is 1/4. And the average here is also 1/4, just because, again, there's only going to be one component that's a 1. And this one is also going to be 1/4. Okay, so our matrix is going to be an interesting one because we kind of said that if we want to go from R4 to R1, then we're going to need a 1/4 matrix that performs this transformation. So our A matrix is just going to consist of the transformation of each of the standard basis vectors. So the first column is going to be 1/4. The second column is going to be 1/4. The third column is going to be 1/4. And the fourth column is going to be 1/4. And this is once again, 1 by 4 vector. It has one row and has 4 columns. And so if we take this and multiply it by a vector, just to make sure that we got this right, so if we have x1, x2, x3, and x4, we can see that x1 is going to be multiplied by 1/4, x2 is going to be multiplied by 1/4, x3 is going to be multiplied by 1/4, x4 is, and we're adding all of those together. So we're going to get exactly 1/4 of each of these values all added together. And there is our transformation matrix. So there's really no limit to what we can do with these transformation matrices as long as our transformations are linear. Let's go ahead and take a look at one more. So just to illustrate that we could transform from any dimension to any dimension we want. Here's an example of where we're going from a lower dimension to a higher dimension. So this we can kind of imagine as we're going to take a two-dimensional vector, and that vector, could be say that, and what we're going to do is we're going to transform it into three-dimensional space. So maybe here that vector is going to point right there. And again, applications in data and data science may dictate why we would want to do this, but in this case, we're going to input two values, and what we want to report is twice each of the values, and then the difference between x2 and x1. So in order to do this, we're first going to see that our transformation starts off in R2 and ends with a vector in R3. And so our matrix is going to end up being 3 by 2. And let's see how that transpires. So here we need to transform two vectors because we're starting off in two dimensions. So we're going to transform the standard basis vector 1, 0, and we're also going to transform the standard basis vector 0, 1. And the transformation of 1, 0, well, let's see what that's going to look like. In the top component of this output R3 vector, in the top position, we have twice the x1 value. So the x1 value here is 1, twice that is 2. And then in the middle component, we're going to have twice the bottom value, and so twice 0 is 0. And then in the bottommost component, we're going to have x2 minus x1, which is going to be the bottom component minus the top. So 0 minus 1 is negative 1. We're also going to do this for the 0, 1 vector. So twice the top component is 0, twice the bottom component is 2, and 1 minus 0 is 1. So in this case, we have in our A matrix, and just we're going to verify that this works out, in our A matrix, we're going to have 2, 0, negative 1 is the first column, the transformation of the first standard basis vector, and then the second column will be 0, 2, 1. And so now this is a 3 by 2 matrix as we had predicted, and so this is going to get multiplied by two-dimensional vectors, x1 and x2. So let's see what happens here. So x1 is going to scale the first column, which will give us 2 times, not 2 times, x1 times 2, 0, negative 1, plus x2 times the second column, which is 0, 2, and 1. Now if we add that together, we'll have, in the top, we'll have 2x1 plus 0x2, which is just 2x1. In the middle component, we'll have x1 times 0 plus 2 times x2, which is just 2x2. So far, so good. And in the bottom component, we have negative 1x1 plus 1x2, which is really just x2 minus x1. And so we have successfully conducted that transformation. And so as long as we, first of all, think about what dimension we're starting in, what dimension we're ending in, that gives us a good sense of how big the A matrix is going to be. And the vectors that we're transforming or performing the transformation on are going to be the vectors that are being inputted into this function. And so each of those inputs will generate, in this case, a vector in R3.